Hello, welcome to this panel discussion on the S8 tension. In the video we have 5 experts who are experts on various aspects of S8, discussing what it might physically mean and various ideas for possible resolutions of it. These 5 experts are Amon, Alexie Leauthaud, Giovanni Aricò, Ian McCarthy, and Vivian Poulin. We did this panel slightly differently to a normal panel discussion. The 5 experts actually had 2 rounds of text discussion before sitting down for the recording. In that text discussion there was also Catherine Heymans. The hope of this was that when they came for the recording, there would be a better starting off point, and hopefully you'll notice this in the video. The video is meant to stand on its own, so you don't need to read the text to follow the video. However, the text discussion will be available to conference participants and possibly the whole cosmology community, and if so, a link will be in the video description. Video is broadly grouped into 5 pieces: a short intro, a discussion on what we're learning about physical cosmology if we take the tension seriously, for example, its scale and redshift dependence, then a discussion of what systematics and modeling are the most relevant in 2023, then a discussion of possible new fundamental physics that could explain the tension, and then a look to the future. So yeah, what is the S8 tension? How tense exactly is it? And what is the state of play in 2023 with the various probes?
So a summary of the S8 tension. The S8 tension is a apparent disagreement between S8 predicted from the CMB and S8 as measured from low redshift probes. And the tension is currently at the 2 to 4 sigma level. Interestingly, it's seen in multiple different possible probes, but not necessarily all of them. So depending on whether you consider RSD, weak lensing in the form of cosmic shear or GG lensing, or galaxy clusters or CMB lensing, the difference is more or less apparent. And again, it's at the 2 to 4 sigma level. There may be some scale dependence, which we will talk about, and redshift dependence isn't necessarily very well constrained.
Just in case someone is completely unaware of what S8 itself is, it's a combination of the sigma 8 parameter, which is itself a bit obscure, which essentially just measures the amplitude of the spectrum at 8 megaparsecs, and omega matter to the power of a half, I guess, which is supposed to kind of hone in on the, I guess, cosmic shear most sensitive directions, so that the S8 omega matter contour is not degenerate. It's a nice circular blob. But I think all of these panelists might be in agreement on S8 not perhaps being the best thing, which we'll get into later on. But this is the framing that the community is currently using for this tension, so we wanted to introduce it that way. So yeah, which measured probes indicate the tension with the primary CMB, and which ones aren't?
Yeah, I mean, I've been watching this for about 10 years now. I think perhaps the first indication might have come from cluster counts with the Sonia-Zoldovich effect data measured in the Planck primary CMB. That was the first place I became aware of the tension. And it wasn't long after that that CFHT lens results showed something similar, and I think that sort of progress with time, of course, galaxy lensing and so on. I think the tension, yeah, has been around for the better part of a decade now, and as Alexie was saying, sort of at the 2 to 3 sigma level. But it's not consistent across all large-scale structure probes. The CMB lensing seems perfectly consistent with the vanilla Planck cosmology. There's interesting discussion in the literature about galaxy clustering there, and I think it's not a completely clear picture. Same thing with RSDs, redshift space distortions. Different studies say different things. To my knowledge, galaxy clusters, the Sonia-Zoldovich power spectrum, a few other things haven't really moved. They've sort of stayed where they're at. Perhaps it's because there are smaller communities with perhaps slightly less active compared to cosmic shear and so on.
Yes, I just wanted to add that maybe here it's important to remind that what we're talking about is, of course, under the lambda CDM model. And so all of these probes do not necessarily, strictly speaking, measure the same scale and redshift. But what we're doing is that we're projecting within the lambda CDM model all of these probes at redshift today and on scale of the order S8. And so this is where it's starting to be interesting, is because if we start digging a bit into it, then it gives us the possibility that there is no systematic discrepancy. It's not just that there are inconsistencies between what is being measured at a data level, but potentially at the modeling level, and how we are projecting from what these things are actually measuring to the S8 plane, the today and S8 sigma scale.
So yeah, Ian, you briefly mentioned not ACT lensing, but CMB lensing as being consistent with the CMB. What other large-scale structure probes are there or aren't there that are consistent with the primary CMB, because I think this might be something that will become more interesting later on.
Yeah, I guess I think for both the RSD and clustering results and the CMB lensing cross correlations with galaxies, there's a bit of scatter in the values of S8 that they get depending on different choices they make. The CMB lensing cross correlations with galaxies, that one to me was intriguing for a long time because it didn't fit the picture that I thought I had in my head, where they were seeing low S8 results. Some analyses were seeing low S8 results, others were not. But I think recently they've been presenting updated, although it's not published, presenting updated results that are now in consistency with Planck. So
I see. Did you see these at like a talk or something?
Yeah, there is a talk that was given at the Kyoto meeting in Japan, where they presented updated results. They said bang on Planck.
I'm actually preparing a paper now based on the Flamingo simulations, and I was looking at cross correlations between CMB lensing and other probes. One that I'm aware of was one done between KIDS and ACT and Planck CMB lensing. So this was Naomi Robertson's study. And I thought there was actually a fairly strong indication from that cross with CMB lensing for a low S8. So it's different than the galaxy clustering cross with CMB lensing. This was a cosmic shear CMB lensing cross that was indicating, if anything, slightly stronger tension than just vanilla sort of cosmic shear, or at least it was quite compatible with it. The error bars were largish, but I think it was still at the sort of 2 to 3 sigma level. And of course avoids the whole issue of biasing and so on. But it wasn't, because the data, they didn't do a tomographic analysis. It was basically the entire KID sample, basically integrated over the whole redshift range, and that crossed with CMB lensing showed a low amplitude.
Does adding BAO to datasets like Planck or datasets like actual clustering measurements have any impact on the tension that is worth keeping in the back of one's mind by like constraining other parameters more closely?
We probably all agree on this, but we have been talking of S8 as this sigma 8 times omega m parameter. The main role of BAO when combined with Planck, well, in fact, even by themselves, just uncalibrated BAO angles as a function of redshift give you an information about the shape of the expansion history, and within the lambda CDM model constrains an omega m parameter. Omega m is very well constrained to be around 0.3. If you add this uncalibrated supernovae data, it's between 0.3, 0.34, something like this. But essentially what we learned from this is that the handle that you need to play with is mostly sigma 8 and not omega m. Again, within a lambda CDM framework. So you need to decrease the amplitude of structure rather than saying omega m is much lower than what Planck predicts.
I think that's what you would need to do if you were trying to move the Planck data. If you were trying to move the Planck results, yeah, that's right, because the BAO is fixing omega m and h. Yeah.
Cool. All right, let's get into this on a slightly more thorough level. At this point, not thinking too much about the data observations and modeling, but about what the tension, if we kind of take it at face value, is telling us about physical cosmology. We'll get to possible beyond lambda CDM solutions later on, but at this point, like, what is it telling us about the redshift, the scale dependence that we need to sort of have in the back of our mind, or possibly even background evolution? Yeah, let's start off by having some discussion and possibly disagreement about what scales the tension is primarily happening at, or what scales are the measurements that are showing the tension primarily sensitive to. Alexie, yeah.
On that topic, I just want to really reiterate what Vivian has said a number of times. I think that there's a lot of scatter in the measurements currently, and a lot is difficult to view clearly because each of the measurements probes a different redshift and a different scales. The scales and redshifts probed by cosmic shear are different from RSD, are different from GG lensing, and yet we sum them all up with a single number. And we haven't really had the ability to do this, but moving forward, I think we're going to want to, in the measurement sense, map out more the amplitude of the power spectrum on a variety of scales and a variety of redshifts. And that scale dependence is very important because some of the theory models are scale dependent, but also we know that many of these systematics are going to be scale dependent. We'll talk about baryons on this call. And so I think that's the real program moving forward, is mapping out this redshift and scale dependence. But to answer your question, Sean, today, do we understand the scale and redshift dependence? I would say not really. From my perspective, I think there's indications of a fairly strong offset on small scales, but whether or not that is the same amplitude as on large scales, I think is an open question. So I think there's a lot more work to be done before we can answer your question.
I just wanted to suggest that we look at a great plot made by Alex just a few, I guess, last month. It's figure 8 in your nonlinear tension 2 paper. I don't know if you want me to share it, Alex. Or I think this is a nice summary of, and we can, disagree on whether all of this is well represented, but it kind of shows the picture, and I really like this figure.
Yeah, so in this paper with a PhD student who's fantastic, Calvin Preston and Georgia Staffiu, and it's a companion to a previous paper that we wrote. So we really tried to sit back and understand and think about each of the probes separately and what they were saying about the S8 tension and what K scales and redshift scales that they were probing and most sensitive to. And I really agree with that point about, it's very difficult to just stack all of these different probes on one S8 plot and to infer what's happening there. So we know from the primary CMB that definitely at high redshifts, Planck seems to leaving all worries about, thinking we're all doing a really great job with our measurements. Planck gives us a really good idea of what the value of S8 is or what the power spectrum looks like. And from on my bias, my side was coming from the weak lensing data, which we have persistently seen these low values of S8 for as long as since I started my PhD. And that's primarily coming from nonlinear information. There's very little linear information in weak lensing and low redshifts. RSD and clustering is kind of in the position right now where it would really help us. So it's super exciting thinking about what Desi and Euclid will say here. But certainly they will help us understand that low redshift regime, but on larger scales. And similarly for CMB lensing cross correlations with galaxies. And CMB lensing, I guess since we put out our first paper, there've been kind of 2 updates that we were kind of like, yes, the CMB lensing results from ACT have come out in consistency with Planck. And so that really starts hammering down your space now, where you'd have to have some modification at some redshifts between like 2 and present day. So it's really starting to slim down the redshift space where we can have changes in physics. But the other possibility, as you can see from the plot, is that it's something coming in from nonlinear scales. And so, Lyman alpha will be interesting here on weighing in on small scales. And the CMB lensing, the other update that's happened in the last year is that the CMB lensing cross correlations with galaxies seem to be shifting to maybe saying that they are seeing consistency with Planck. But that's also a space that I'm really keen on seeing what they say. Those measurements are super cool and very robust.
So this plot makes me want to ask a question based on what I think it was Ian was saying earlier, that there was CMB lensing cross weak lensing, some analysis, but it looks like in this plot there shouldn't be a cross correlation, but or maybe the weak lensing leaks all the way up to 0.1. Sorry, ignore me. There is a kind of little overlap in that tiny little corner of each of the things, I guess. But Ian, you were saying that was showing that a small value of S8, which I guess is a little bit contradictory to what you were just saying, Alex. But how big were the error bars given how little the overlap region is?
Yeah, I don't have I can try and pull up the paper, but I thought that it was at the similar level to what standard sort of cosmic shear was showing, that a sort of 2 or 3 sigma tension. And to be honest, I'm not sure why that hasn't been followed up in DES, for example. I guess you could do this much better with a DES crossed ACT cross now between cosmic shear and CMB lensing, so it'd be good to do that again, have much better signal to noise.
I think that is in review now.
Okay. Is it fair to say that maybe there's a consensus amongst everyone here that if it's a redshift dependent thing, it has to kick in below redshift of 0.5? Then this is because of CMB lensing, and that the kind of cross correlations are maybe a little bit confusing at the moment, that there are some cross correlations of CMB lensing with galaxies that are indicating a slightly larger value of S8, some indicating a slightly lower value of S8.
So I started from like a slightly different basis here. So in our summary, we say that the SA tension is somewhere between 2 and 4 sigma. I would go more from 1 to 2 sigma, let's say, because not historically maybe, but I think that the main drivers of this tension right now is the cosmic shear versus the versus Planck, basically. And we already have seen with our work and also with the new DS plus kids work that this tension is going from 2.3 sigma or 3 sigma to 1.6 sigma when covered with the same framework. And galaxy clustering. We've seen that that CMB lensing is in agreement with the CMB, but also like maybe different modeling of the CMB itself can go to lower S8, like different modeling of the A lens parameter, as Ian was saying in the chat. So I know that I shouldn't say that, but different modeling decision or choices could make this all these measurements a bit closer. And actually, all these measurements that we see here, like in line, they're not really independent, and it's not clear how these add up to like if you have many different 1.5 sigma tension measurements, that doesn't mean that they should necessarily add up to 4 sigma. So, yeah. So that said, I would say like it seems that there is a bit of difference between higher redshift, larger scales, and lower redshift and small scales. So it seems that there is at least some inconsistency, maybe in the analysis, maybe there is some physical things, but at this level of the precision of our data and accuracy of our modeling, I mean, I don't think we can really tell if there is something physical or tell apart something physical from our real analysis choices.
I just wanted to chime in on the multiple probe thing to say that as we look to constrain more this redshift and scale dependence, we might consider, this might be controversial, I don't know, we might consider moving beyond the way in which we analyze things in a typical like 3 times 2 point or 6 times 2 point or n times 2 point, because oftentimes the things that are thrown into those analyses probe different scales and different effects. Combining cosmic shear with CMB lensing of galaxies on large scales or DG lensing on different scales or RSD, they're all probing different parts of this plane. And so when we lump them all together that way, it makes it more difficult to disentangle. So I'll just throw that idea out there.
I really agree with that. I find it really exciting when we look at this plot to think about all the upcoming data sets and we're really at the brink of filling in these different, I've tried color coding these in another version of the plot in terms of their S8 value, and we're kind of just playing this game of filling in these puzzle pieces and totally agree that means that then quantifying these things as I think Vivian and Alexie have both said, in terms of S8 is just confusing the picture a little bit more than it needs to be. I think the trick that we found what we found is difficult is we've tried like taking the weak lensing data and reconstructing the power spectrum, but we're just nowhere near the data we need to be able to do that from weak lensing alone. And so the only way we were getting traction is by, like what we did in this paper, is by fixing the cosmology on large scales at Planck, which is then making a hypothesis that that's accurate, and that's obviously an assumption at this point. And then trying to reconstruct the nonlinear power spectrum. But certainly in the next decade, with the data we'll have, that is, I think that's a really powerful way to go.
Giovanni, you mentioned the weak lensing and you mentioned the primary CMB and the CMB lensing, but I know, again in the text chat, so someone please elaborate on this now, the other probes were measured. And Ian, you mentioned it in the intro, like galaxy clustering and...
Galaxy clusters, I have in mind, for instance, a recent analysis of the Rosetta clusters that is in agreement with Planck, if I remember correctly.
Yeah, it depends on how you measure the mass bias or what you use as a value for the mass bias.
Cool. I think if anyone is unsatisfied with the conclusions we're reaching, that we should have dived even more deeper into the multiple probe sort of thing, this is exactly what Cosmology from Home's live discussion is. So if you're sitting there, ask some questions in the Mattermost and then come to the live discussion and we can carry on this discussion. Let's just talk briefly as a group now about Lyman alpha. Obviously, in this plot that we're looking at from Alex's paper, it's like it's the missing quadrant, right? Like we've got the bottom left, the bottom right, the top left, and we don't have the top right. I don't think we have any Lyman alpha experts here, but what's stopping Lyman alpha from actually being filled in here? Why have we not got these constraints?
I'm not an aficionado. I've just sort of been watching the literature as it goes by. I mean, there are constraints from Lyman alpha on these scales. I mean, it's most predominantly used to try and test CDM on the very smallest of scales. So lots of discussion around warm dark matter mass constraints and so on, running of the scalar spectral index. There hasn't, to my knowledge, been well, this is, again, not as an expert, but I haven't seen a lot of cross comparison with the cosmic shear and so on to discuss this in the context of the S8 tension. It's clearly relevant, though, because it's, as you show here, it's probing small scales. This is a very difficult thing to model theoretically. You're talking about cold neutral gas that's on the very smallest of scales. There's interesting discussion in the literature about the role of baryon physics and so on. Certainly the thermal history of the universe is something you need to know very accurately to be able to model this. It's a resonant line as well. So there's lots of very bright people working on this. And I think just the focus of the community is probably more on the nature of dark matter. Most of the attention's gone there as opposed to the S8 tension and so on. But clearly we need to bring the communities together to sort of see if we can come up with something that combines the strengths of the probes.
Yeah, if you're a Lyman alpha physicist and you're watching this and you look at this plot, look how important you are. Like the S8 tension is the second most talked about thing in cosmology at the moment, and probably the most talked about because H0's been talked to death. So join the discussion.
So yeah, I mean, so at the moment, as far as Lyman alpha goes, I should also say that I am not at all an expert in this, but there is two to three main datasets that are being used. There is the EBOS Lyman alpha. This is what we're looking at now. This paper is analyzing the EBOS Lyman alpha data. And in this paper, he defined that EBOS is a bit low in amplitude, essentially, as a bit of a low sigma 8. And the way they can interpret it when they do a combined fit with Planck that would fix the large scale is to say maybe there is a change in the tilt, so some sort of running, or really what they even did was to say, let us assume that there are two tilts, one that is valid at Planck scale and another one that's valid at Lyman alpha scales, which in these datasets is like maybe around 1 in H inverse megaparsec scale. Because if we put everything in the sigma 8 plane, this is where it gets a bit muddy, because we're projecting from a smaller scale back to the sigma 8 plane, but it looks like, just look at this, it sort of looks like they have it's like there is an offset in omega m in this parameter space. But I just think this is because we are trying to project small scales that have a different amplitude to larger scales, and then assuming a lambda CDM like cosmology, and then that's what it's telling us. It's just showing us that there's some mismatch between the lambda CDM prediction of Planck and that of Lyman alpha. And I think a better way of looking at this tension is shown in a summary figure of a different paper applying Lyman alpha data to the issues related to early dark energy and so on. But if you go to the very last figure on this paper, figure 9, and you look at the top right insert, but this is sort of a summary of the situation of the Lyman alpha data to my knowledge. I'm happy if during the discussion, live discussion, people want to correct me. You're looking at a plane where you have the tilt of the power spectrum NL measured on Lyman alpha scale and at redshift of Lyman alpha. So we're talking redshift 3, and scale, I think it's 5 or somewhere between 1 and 5. I forgot the exact number, but maybe 3. H over megaparsec versus amplitude. Delta L square is the amplitude of the power spectrum. In the shade, the full gray contour is the Planck prediction. You fit Planck and you say, what do I predict? Now I extrapolate to Lyman alpha, so you sort of do the reverse engineering. You're saying, what do I predict for Lyman alpha at this scale? And then you measure it with Lyman alpha in blue and in red. The EBOS data that Alex was just mentioning are the blue curves that are a little low in amplitude. So delta L is shifted a bit on the left, and have a different tilt. NL is a bit down. And then there's another set of data called this XQ100, and there's something called Mike Iris. I mean, anyway, so two sets of Lyman alpha data that's probably even smaller scales. And those are okay with the amplitude. So delta L is about the same, but NL is much lower. So bottom line is both sets of data seem to indicate that there is some sort of suppression with a different tilt at scales measured by Lyman alpha data and at redshift 3. That's the bottom line. And it's in disagreement with what Planck would predict.
I haven't seen this plot before, but if you scroll further down, I just noticed then their S8 sits bang on Planck as well. Can you comment on that, Vivian?
Yes. I mean, so this is where the point is now you're using a different amplitude and tilt to predict much larger scales than what you are measuring. So if you actually just look at EBOS Lyman alpha alone or XQ100 Lyman alpha alone, these are all combined with Planck, and this that you're looking at. You would even find that I think if you were to analyze EBOS Lyman alpha, I'm going to say something wrong. I think they are a bit low, the EBOS Lyman alpha, and XQ100 is actually a little high in S8 because you're using much lower amplitude scale and you're extrapolating back towards this scale. So if you were to just look at analysis of these things by themselves without combining, you would find EBOS a bit low, XQ100 a bit high, and I think once you add, I guess, constraints, because this is baseline plus, when you start to add large-scale constraints from Planck and DAO, you're just losing all the constraining power from this data on the scale.
Last thing we wanted to talk about in this section was supposed to be this consensus amongst you that S8 isn't the best framing, and this has kind of been coming up regularly when we're talking about, because I mean S8 is what this 0.1K kind of thing, but these things are not only sensitive to that. And do you have some ideas for what, let's say someone who's not in this group of 5 people is doing a cosmic shear or CMB lensing or Lyman alpha or RSD or clustering or whatever analysis, and they want to talk about the thing that is currently called the S8 tension? What statistic or statistics should they be reporting? Can we make some suggestions, and can we get a shift in the social norms of the community to something that we think is more interesting or elucidating?
I think even before getting to new statistics, an easy step that I think like the ACT lensing team did an excellent job at is identifying when you quote your constraints, which K range and which redshift scales you're probing best. And that's kind of new, that shift, and something that I think is excellent moving forward, so we can really start fitting in this puzzle.
Yeah, no, I would echo that. I was just going to say that because the lambda CDM is so, interwoven in everything we do, you only need 6 parameters to specify it. The natural thing is to compare the parameters. We don't do things in sort of a non-parametric way where you just sort of say, this is the amplitude measured on these scales. And it's not so easy to do because it is a convolution over different scales and redshifts and so on. So I suspect that's why S8 is the thing. We haven't been able so far to come up with an alternative that's as catchy and so on, but it definitely requires thought because it is simplifying the problem. We see, well, you can tell that the inconsistency between the results of different probes tells you that there's a scale dependence and probably a redshift dependence. So I think Alex is right that it's good to indicate that. Whether we can take a step further then and somehow plot these things on the same plot as Alex has attempted to do here in Figure 8, but to put some points with error bars or something like this, that would be nice to be able to do that. I
guess you often have these 1D like lines. I mean, a bit like what you've got on the left of this exact same page, Alex, but with more than just kids and dads. With everything, the TSZ, the galaxy clusters, the blah 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 blah. Perhaps it would be useful to do exactly what you're talking about, Ian. Instead of plotting something like that, plot what you've got kind of on the right with the. You could still just have the 1D S8 constraint, but just placed in KZ space, if that makes sense.
Yeah, no, I mean, I just wanted to echo that again. And one thing that I think would be useful, but it makes it harder to compare between experiments for sure, but to compare to lambda CDM is still useful, would be to simply project using a window function that instead of being this top hat 8 megaparsec scale would be the window function of the survey, centered around the scale of the survey. And then as far as the theory prediction goes, it's trivial to use whatever window function you've used. So essentially what I'm saying is, instead of S8, maybe use S1 for weak lensing, then S8 for galaxy clustering or whatever, and then see, compared to the lambda CDM prediction, how this is evolving. So it's sort of just saying what we are looking at redshift 0 in Alex plot. Just look at that. Project that at the relevant scale and see whether there is a tendency compared to the lambda CDM given various probes to have a decrease.
Would one want to also change this omega matter power, like instead of it being omega matter to the power of 0.5? Because if I understand correctly, the different observables have a different exact dependency on that.
Yeah, agreed. I mean, it wouldn't be. It has to be whatever. It's just you're losing the ability to compare each experiment to one another in a sort of model infinite way as we would like. But you're saying, my experiment, I'm going to extract the best scale, the best degeneracy that I can, whatever, and I'm projecting that onto. Well, I'm constructing that quantity, and then I'm just doing the same with the lambda CDM projection.
Yeah, I think it's something along the line that Vivian already spoke about. So S8 was like built, let's say, to optimally fit the cosmic shear analysis, because it's for the degeneracy that we see in cosmic shear, but that is not the case for other probes like galaxy clustering, for instance. So it's not only a matter of scales, but also of degeneracies between the different parameters. And probably one thing that we could do, and actually it has already been done, I think maybe the Dark Energy Survey started this, is just not to compare only one parameter, which is S8 in this case, but compare the full data set. So like is DS fully compatible with the with Planck, for instance? And this is the statistics they call suspiciousness, right? So it's not comparing just in one parameter, but like the full, in a Bayesian sense, the full data set, like given some priors and given the posteriors. It's more difficult because you have to jointly analyze both the likelihood in this case, but I think it's a fair way to assess tension between two different data sets.
When on the window function idea from Vivian, I very much agree for the upper scale dependence, but it's not just the window function, because surveys often impose also an R-min, a smaller cut. So you need, when we compare with theory, we need not only the window function, but the smaller scale cut. That's a side note. But then the other point I wanted to add here is that in this plane, there's another axis which we haven't talked about here, and I think we need to add, which is the halo mass dependence. Because something like galaxy clusters and cosmic shear may probe the same scales, but they probe very different halo masses. And the reason that's relevant is because something like baryonic effects probably has a halo mass dependence. And so if we're seeing something like baryonic effects, it would show up differently for clusters and cosmic shear. And so I think when you consider that systematic, there's this other axis that would be really interesting to add.
So yeah, I'll take the last word, which is that what would be really cool if, after the live discussion of this at Cosmology from Home, if the community of Cosmology from Home and these experts here today could come up with just like, I mean, there's lots of different suggestions now, and if we stick with 10 suggestions, none of them will be done, but maybe one or two, even if we're sacrificing breadth for specificity, one or two things that might improve the reporting, and then try and encourage the entire community to do that one or two things instead of just S8. That'd be awesome. But we won't try and do that right now, because we want the rest of you to have a chance to share your thoughts. Okay, now let's move on to systematics and modeling. So the idea now is to be kind of moving into the what stuff in the context of observations is are the relevant systematics, but just the things that if you want to understand the measurements in 2023 and what people are worrying about and moving on to next, are the things that one should most be caring about now. So it's not just things that might be wrong, but also just what needs to be done to improve them. Cool. So let's start off talking about baryons and hydrosims as a kind of joint topic and how we want to start constraining them. I guess Flamingo did come up as a new hydrosim that maybe many people aren't aware of because the paper was literally on the archive like a week ago or something. But
well, I can talk about Flamingo. I mean, it might be. Well, can I maybe spend 10 seconds sort of generally motivating in hydro simulations and then talk about Flamingo? I mean, the issue, right, is that traditionally we've been using gravity-only calculations to do our theory. And so we're probing into the deep nonlinear regime, and up until about 5 years ago, maybe, we've been doing this ignoring essentially all of the physics that goes along with galaxy formation. So just doing gravity alone, no electromagnetic force, no associated galaxy formation in physics. In the meantime, other people have been studying galaxy clusters and how galaxies form in the context of hydro simulations and comparing to the galaxy population. One thing you immediately conclude is that feedback is an important part of regulating how galaxies form. We see observationally huge amounts of energy being dumped into the gas in the form of jets and winds and so on. And it didn't take long for galaxy formation people working on the simulation side to start thinking, well, what does this do for, for the larger scales? What impact, if any, does it have on the cosmology question? And yeah, so I think perhaps Joop Shea and Marcel van Dalen amongst the first people who back in 2011 did an initial study of this in the context of the OWL simulation. So these are simulations where they were just playing with things, varying the amount of energy you dump into the gas and how it's distributed and so on. And depending on what you did, you could get quite large effects. And so that was the first indicator there that we needed to worry about this for things like cosmic shear. What also became clear, though, well, tied in with this, is that the answer was quite sensitive to how you did things. And so the concept of calibration then developed. And so calibration had always been sort of part of the understanding galaxy formation, but now it was sort of entering into the context of cosmology and large-scale structure. And so that's where I think Bahamas and Cosmology, a few other simulations, Fable, started to pay attention to observables that you might want to calibrate on if you're trying to understand the impact of baryons on large-scale structure, in particular the mass fractions. If you wanted to get a good sense of how much feedback were going to affect cosmic shear, you'd like to know how well do halos maintain their baryons. So that was the idea behind Bahamas, was to try and calibrate against the gas fractions and stellar fractions of groups and clusters. What Flamingo has done now is taken the next step. Number one, it's gone to much larger volumes than Bahamas, so you can compare it against all manner of different large-scale structure probes. So these are gigaparsec volumes. Furthermore, we've been much more systematic in looking at our variations. So we're using machine learning to do the calibration of the model, but also to not just pick the best model, but also a range of different behaviors around that sort of factor in observational uncertainties. So we basically can map out a range of sensible models and make predictions, run the simulations, and compare it. So that's where Flamingo has come in now. The other big advantage, of course, is that because the volumes are so large, we're making on-the-fly light cones. So you make full helpix maps of lensing of the Sun-Yesel Doge. All this stuff is produced, so it's right there for observers if they want to analyze it in an observationally consistent way. Yeah, so I think the tools are still there. There's plenty of steps to take on this. One of the disadvantages of the hydro simulations, they're very expensive, so you can only do a finite number of realizations. So I hope Giovanni will talk about his Baco emulator, and there's also Halo models, which are physical modeling tools that can use to sort of take insights from the simulations, but also generalize them and do things that way. So it's a nice complementarity, I think, between the hydro simulations and these parametric models that Giovanni and Alex Mead and other people are coming up with. Yeah.
Yeah, I mean, I think Ian already told most of it. So he explained how playing with hydro sims you can you can try model really physically how hydrodynamical processes and cosmology are intertwined. Whereas with more parametric model like the Halo model of Alex Mead or that is HN code, or the baryonification of Aurel Schneider and myself, you can be a bit more flexible in the sense that you can put in halos, you can inject in halos whatever density profiles you want, and then check how this reacts on the total matter power spectrum. So this is powerful because you can try a lot of different models in very small amount of times, and you can, for instance, calibrate directly with observations. If you have any of density profiles that you get from, for instance, X-ray or ST. So it's a way of calibrate directly your theoretical prediction with your model, with observation, sorry. Whereas maybe for hydro, it's more complicated because you have to run the full hydros. And only recently, like, they're managing to calibrate in a better way these huge hydros. So maybe Ian didn't mention it, but Flamingos has been calibrated with using neural networks, emulators of Gaussian processes, if I remember correctly. So this is a way, like typically hydro sims were calibrated end-wavely or rule of thumbs, or try and error. With these Gaussian processes now we can calibrate it way better, and this is also an improvement for theoretical modeling of baryonic processes. And something you have more easily done with Elo model or with baryonification. But just to finish, I completely agree with Ian that these are complementary models, and it's very cool that we can use all of them together and try to infer, like to get if they are in agreement or in disagreement. So it is better to understand what's going on.
Cool. And is this something that, I mean, I hesitate to say it's straightforward, but at least at the one step out of the weeds, it's relatively a straightforward idea of what's happening. You have HMX code, or you have baryonification, which is a kind of model for how baryons are doing, which now has a bunch of free parameters that can be simultaneously marginalized over with omega matter and S8 or whatever one wants to have instead of S8. And you just kind of measure your baryons that way, and with codes that are trusted, with models that are trusted because they can match simulations like, I guess now Flamingo has become the cutting edge as of a few weeks ago. Obviously, once you get into the weeds of like what is the correct model, blah, 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 that becomes very non-straightforward. But is that kind of framework the way that this has to and will proceed, I guess?
Yeah, I mean, I think it's the way to move on. So we have great deal of different observations in multi-wavelengths. So we have X-ray surveys now coming online, like Rosita. We have S3 surveys. We have even cosmic shear, which is telling us about what we think is the suppression in the matter power spectrum with respect to gravity only. So we can turn the problem on its back and try to infer baryonic processes directly from cosmic shear, and we can try to combine all these probes and try to get physical understanding of these baryonic processes. And this we can do with Halo model. This we can do with baryonification or with hydros. The important thing is we have the flexibility to model all of this, and important thing is that we have some models that are fast enough to do the analysis. That's also a point, and predictive enough.
Bring up one thing, Ian. You mentioned in the text chat that you wanted to give a shout out to the measurements of the TSZ effect power spectrum, and I think this is it was in the context of this part of the conversation, which I found very interesting. They're probing very massive halos, you say, which are baryonically closed. I guess you mean that the halo is so massive that even intense processes can't eject the baryons because the gravitational well's so deep.
Yes. I mean, that's right. So, the SZ power spectrum is probing 10 to the 15 solar mass. This goes back to what Alexie was saying. It's probing similar scales to cosmic shear, but much higher masses. if you look, so these are the most complete systems we know in terms observationally. We're not missing galaxy clusters out of Planck at this mass scale, and we have very well measured pressure profiles and all kinds of things. They are baryonically closed. So, from the point of view of ejection and messing about with the matter power spectrum at this scale, I don't think it's I don't think baryon physics are responsible for anything that could be going on here. I think it's more of an observational issue, that it's not totally trivial to extract SZ thermal Sonia-Zeldovich data, to isolate that even in Planck data, because there are multiple different sources of radio emission. Of course, you have the clustered infrared background, you've got radio sources, you've got KSZ, all these things are there. And so it's more of an observational challenge to sort of isolate this component in the CMB maps. But if you can convince yourself that you've done that, and people have put in a tremendous amount of work on that, and the results haven't changed over the last 7-8 years, then you have something that I think is as close as bulletproof as you can from the baryon modeling side. What I found quite interesting is, so SZ power spectrum, again, sensitive to 10 to the 15 solar masses, cosmic shears 10 to the 13, 10 to the 14, and then you have SZ cosmic shear cross spectrum, which is what Tilman Troster was looking at in his paper, and that sort of probes an intermediate regime. So the combination, that they were referring to it as a triad, but these three different possible auto and cross correlations will probe the full range of mass scales, and you should be able to pick out a scale dependence, a halo mass dependence, and possibly a redshift dependence just by looking at these things. My understanding of the current observational picture is that SZ power spectrum by itself is most in tension, the SZ cosmic shear is next, and then cosmic shear is the thing that's sort of least in tension. So if you interpret those things literally, it looks like the most massive halos are less abundant than they should be compared to Planck. Planck CMB SZ results say you're missing about a factor of 2. So the factor of 2 less 10 to the 15 solar mass halos in the data compared to what there should be if the Planck cosmology was correct. And that difference decreases as you go from 10 to the 15 down to 10 to the 13 in cosmic shear.
Yeah, I'll just weigh in on something that Ian said in terms of constraining the halo mass dependence. There's an additional way, which is something my group's been exploring for a couple of years. You can look at papers by Song Huang and company. But we think we can divide galaxies by mass and probe this whole mass scale to constrain the halo mass dependence. And the key insight there is that cluster finding, optical cluster finding, is often limited in terms of how far it can go down, whether it's lambda 20 or lambda 15. And we have papers out there and some new work in prep showing that with galaxies we can push quite a bit further down and thereby constrain the halo mass dependence of that effect independently of the other methods that you mentioned. So that's something that I'm personally super interested in.
So Ian, this is a figure from 2013, and are you essentially saying that kind of Planck hasn't improved since 2013, I guess, in terms of...
Yeah, that's right. Yeah. So there is a Planck 2015 paper on clusters, but and the tension is even a little bit larger. The error bar is a bit smaller. But I just like this plot because it shows you just the number of clusters you expect versus redshift. They didn't sort of show it in that way in the later paper. It just shows quite clearly that so that the dashed green line, the top line, is what you would expect for the number counts, given what you think the mass bias is, which is the weak lensing constrained stuff from Henk Hoekstra's group and other people. So that's what you would expect. The red points are what you see. However, if you're prepared to invoke a much larger mass bias, then you can get around that. But it's much larger than what stack weak lensing observations show, and certainly much larger than what hydrodynamical simulations show. This is the SZ number counts. The SZ power spectrum there is no mass measurement in that at all. That's just a map of the fluctuations in the Compton-wide map. And that gives a very similar answer in terms of what the implied sigma 8 is. So You can compare a hydro simulation directly to the SZ power spectrum without going by halo mass at all, and you find exactly the same thing. The Flamingo paper I'm writing right now shows it sticks out like a sore thumb. Actually, the SZ power spectrum is way off, but it's hypersensitive to sigma 8. It's talk about S8 as this parameter that describes cosmic shear very well. It doesn't describe the SZ power spectrum very well. The SZ power spectrum is much more sensitive to sigma 8 than it is omega matter. The scaling is steeper. It almost exclusively picks out sigma 8, actually. It's very nice from that point of view.
Yeah, I guess this is very interesting in the sense that if you wanted to explain not the S8 tension, but the why is in general some combination of sigma 8 and omega matter slightly low with just baryons, you'd run into a brick wall here, I suppose. But perhaps you could still claim that there's systematics everywhere, and that this maybe mass bias is the problem here, and other things are the problems in other things. But then I guess, yeah, there does have to be this fluke alignment that all of the systematics are pushing things down rather than some things being too high and some things being too low, which maybe is the case. It's just a bunch of coin tosses.
I mean, Giovanni mentioned the E Rosita. So E Rosita is measuring much lower mass systems where the selection function isn't nearly well defined as it is for the Planck SZ. This is a very clean selection. It's a mass limited selection, and it's very high mass halos, whereas E Rosita is probing into the group regime. So there, the question of baryons becomes much more relevant, I think, for the E Rosita stuff.
Can the S8 tension be completely solved by several minor effects? I guess everyone agrees that it can be if it's maybe it was pushback against from multiple directions about how many of these minor effects there actually have to be, and how weird it would be if all several minor effects were all pointing in the same direction. I mean, Giovanni, I get the feeling you were talking more or less specifically about cosmic shear, but
yes, yeah, but I think also cosmic shear is one of the probes which is more in tension with Planck, right? So if galaxy clustering is already 1.3 sigma in tension with Planck, like you don't even need like specific minor effects to push that, because this is not really a tension, because it's just 1.3 or 1.4 sigma. So in cosmic shear, I think there might be some kind of systematics which are not independent from survey to survey. For instance, I don't know, if we are not taking into account correctly the nonlinearities in our matter-Poe spectrum, this might reflect in all the analysis that we are doing. So if we are saying, like, currently we are taking HaloFit or HENCODE or whatever power spectrum that we are using as a perfect model. So we are saying this is no error in any of the in any scales, nor in any cosmological point that we are evaluating. But this is not really true. So we know that the HaloFit is an error, and we are not really taking into account. So in our analysis, we are using, instead of HaloFit, Bakoimu, which is much more accurate, and we are seeing that it's a 0.4 sigma shifts with respect to the HaloFit analysis. And this is just one example that might be like not taking into account our model are not perfect, might be playing a role in exacerbating a bit this tension, which is not anyway, to me, is not anyway big to start with. So this might just get lower and lower when we consider all the theoretical errors and modeling assumptions that we are considering now.
I think our landscape, speaking on weak lensing specifically, our landscape is constantly changing. So for Désier 3, we rapidly and unexpectedly for me found ourselves in a position where we were model systematics limited, and so many of these intricate dials that we thought of on the data calibration really just weren't impacting us, and we were losing, almost a factor of 2 in S8 power because of model uncertainty. So I'm not. Certainly the approach that we take, for example, in DES, and we're rethinking now as we're doing our Y6, but I think it will be similar lines, is that we take all of our systematics that we can think of in the model, and we say, okay, let's estimate there's about 10 of them maybe. This was the Y3 case, and let's allow each of them we allow some wiggle room of 0.3 sigma. And 0.3 sigma is small, right? For me, in my opinion, when I see a model shift causing a 0.4 sigma, that's a small worry. And obviously, when we're talking about tensions that are between 2 and 4 sigma, that becomes a bigger worry. But if we're just talking about the accuracy of your results, so we say that we can tolerate this many systematics, and so each of them, we're going to let them have 0.3 sigma bias wiggle room and let that stack up to 1 sigma. And we're going to have to think about this again for DESI, for DES year 6, and for DES year 1, where I guess the landscape might rapidly change again, where we go back to being observationally systematics limited, but certainly for DES year 6, we will be model limited again. And the truth is that for some of the model choices, like the one that Giovanni described, like the nonlinear matter power spectrum modeling without baryons, you can kind of see a right and a wrong answer. This is what we try to separate in our kids plus DES analysis, that you can see a right and wrong, and it's quite easy to make a choice. But the reality is that for baryons and for IA, we still have a lot of uncertainty without new observational constraints. And for those, I think we do have to start thinking about adding in a systematic error, or but there are lots of different opinions on that when we discuss this every week in DES year 6. So I guess we'll see how the field moves in the next year or two.
Cool. I guess one thing that was brought up in the text by someone, Alexie, I guess you brought this up, that multiple doesn't equal does, or doesn't equal possible doesn't necessarily mean actual. This idea that, yes, okay, there are a series of possible different modeling choices that could reconcile the tension if all of them lay on one side, but that doesn't mean that they do, right? Like, and as I guess Giovanni and Alex both emphasized, there are some systematics or modeling decisions where it's clear which one is the better one, but there's some where they aren't, and where there isn't, yes, okay, you could make decisions that reconcile the tension, but that how do we know a priori those are the better ones? I guess if you have a strong pro lambda CDM initial bias, then, or not bias, but prior probability distribution, then okay, you're probably going to say it's the ones that reconcile it that are the most likely ones. But if you don't have that prior, then maybe.
Yeah, I'll give some context to my comment, Sean. I'll phrase this in terms of something I know well, which is the galaxy-galaxy lensing measurements. And in that context, we look at the scale dependence of the GG lensing measurements, separate from cosmic shear. And I think it's clear, it seems pretty strong that the amplitude of the GG lensing signal on small scales is low. That's what I've sometimes called the lensing is low problem. And on larger scales, it's also possibly low, but with lower signal to noise. And so the small scale question, you can probably resolve with multiple different effects. If you put them all together, assembly bias and baryons and other such things. But we're at that stage where we don't know whether there are multiple effects on small scales that are contributing that could resolve the problem, or if it's the same question as on large scales, and baryons are smaller than baryons and assembly bias are not a problem. So I think we're going to make a lot of progress on these fronts as we continue to analyze the data, and I think we're going to try to constrain baryon effects. That was our previous discussion. We'll try to constrain assembly bias, and so we'll try to constrain a lot of these observational systematics, and then that will give us a much clearer picture as to what degree they contribute. That's separate from the theory modeling question, which we just discussed, but in terms of the observational ones, I think we can make some progress there.
The other thing I was expecting people to push back with is the claim that cosmic shear is the biggest tension. I mean, Ian has already kind of pre-pushed back against that by saying, for example, maybe the galaxy clusters, not clustering, but clusters, are the biggest tension. So Giovanni made the claim that cosmic shear is in the biggest tension. Maybe it's in the biggest tension of the probes that we trust the most, kind of in a wishy-washy way. CMB's trusted the most, and cosmic shear is trusted more than galaxy clusters in some kind of social consensus, but the individual people who work on each of these experiments trust their own ones more than the other ones. But yeah, Ian, I guess you were saying that clusters are in more tension than cosmic shear.
Yeah, well, I think it's a similar situation in that there are relevant systematics there as well. Statistically, the statistical error bars are smaller in the sense the tension is formally larger. But the systematics are there, and I think part of the reason why we're all talking about S8 and cosmic shear is it's a larger community with big surveys are on right now. I think eRosita might have changed that, but unfortunately, things haven't panned out so well with eRosita because of nothing they've done wrong, but just political issue there, but that may change again soon. We'll see what happens. But yeah, I mean, formally, the tension I think is at least as large, and it's just a question of whether who do you think has better control of their systematics and so on. And there's also an aspect of just the sizes of the communities and how loud one community is relative to another. And I think the cosmic shear people are very loud relative to the cluster people. I think probably cluster people have gone back in their shells a little bit, left with this conundrum. They don't really understand what's going on here, and nor do I. So I think they've gone back to understand that AGN feedback works, but it's that problem hasn't gone away.
Very quick, super quick. So I just wanted to say, even if the effects don't align in the right direction, still you have a decreasing of the tension, just because if you include the errors that are associated to the different models, then like your tension just decrease because you have a larger error bus, if you want, like more error. Just that.
Okay, so maybe there is some consensus on the following thing, which is that of the unknown sort of modeling issues, perhaps the nonlinear physics is something that can be modeled just more accurately. We know what Newtonian gravity is, we just have to run better codes. But intrinsic alignment seems to be something that people are in consensus that at the moment it may be even the leading modeling, systematic's not the right word perhaps, but modeling uncertainty in cosmic shear at least. So I guess this NLA versus TET as two different intrinsic alignment modeling was something that came up in this text discussion quite a lot. But perhaps the consensus by the end was that both of them are being used outside their region of validity, in which case it seems as an outsider, the consensus you guys were reaching is that we need to have new intrinsic alignment models that are actually relevant for the scales that they're being used at. Can someone please quickly summarize the NLA versus TET situation, what they are on a very high level, because we don't have time to get into the weeds, and what they're saying that's different, and then we can go into what needs done for new intrinsic alignment models?
So I can try. The nonlinear alignment model is the more commonly used model in the literature. It has one free parameter or two free parameters, either some intrinsic alignment amplitude with and without a redshift dependence. The TAT model, the tidal torquing and tidal amplitude, other way around, tidal amplitude and tidal torquing model, it's a superspace of the NLA model, and it allows a few extra terms going to higher orders in perturbation theory. So in theory, as it's a superspace, it should be more accurate on smaller scales than NLA. But as you correctly said, Sean, none of these, I think, in my opinion, are really shown to be accurate enough on the scales that we're using. The TAP model incurs 5 free parameters in the way it's usually used. And so there's a lot of discussion on if you have a more complex model and a more simple model and they give the same goodness of fit, how do you warrant how do you choose which model? And I think we've been having this discussion for 6 years now and within DES. And the truth is it's really hard to decide right now, and it's very subjective until we have measurements on simulations, on the hydro simulations, more direct detection measurements that we can rigorously compare against. And I think in combination with that, we do need new models and new ideas on how to tackle this systematic. I think I would put it up there on par with baryonic effects for cosmic shear leading systematics. Certainly they cost the same amount in power.
But before, Alexie, you respond, when you say they're on the same level, when I look at, say, this recent DS plus Kids analysis that you were an author on, or Giovanni's back or Emo one, it looked like the intrinsic alignment shift was quite a bit larger than the baryon one, maybe a factor of 2 or 3 even.
Yeah, I guess it depends on how you think about it. So if you consider two IA models, two intrinsic alignment models, the NLA and the TAP model, they cause a shift in S8 that is real. It's not a projection effect between like 0.5 sigma and 1 sigma. And they can, and for kids as they do, if you're in this model limited space, they will inflate your error when you move to TAT. So it drops your S8 and it inflates your error a little bit. When I say that systematic that's leading or costing, in that, like in kids plus DES, we took the approach of throwing away small scales and marginalizing over a free parameter from HM code. And so it's really costing our error budget for baryonic effects. If we were to compare, for example, not modeling baryonic effects in kids plus DES with our double down approach, there's a huge difference in S8 as well. So I guess both can cause differences in your value of S8, and they're both really tanking our constraining power that we can get from weak cleansing.
Yeah, I want to say a word or two about intrinsic alignments, but to start, I just wanted to also push back on the idea, Sean, that you mentioned earlier about these community notions about certain probes being robust or not robust. I think Ian's comment about certain communities being loud is very valid. And cosmic shear in particular has a lot of different effects that go into it, including intrinsic alignment. And I think we need to really take those into consideration. So I'm a big fan of galaxy lensing, and in DESI we're going to have some really amazing GG lensing measurements. And one thing we're going to be able to do, we've done simulations to show this, is make measurements that are free of intrinsic alignments by making stringent lens source cuts. We'll have measurements that just are not sensitive to IA, which is going to be a really powerful statement. And in addition, one of the reasons I really like the GG lensing measurements and having them separated from cosmic shear, not lumped into a 3x2 point, is because you can also really isolate the scales of baryonic effects and really clearly see if you have baryonic effects that are scale dependent. So that's something I'm super looking forward to with DESI. And then final word on intrinsic alignments. We are also thinking about DESI 2. I'll mention this in the future survey discussion. But one of the things we are thinking about with DESI 2 is how to design a DESI 2 survey that might be able to get better constraints on IA. And so I think there's possibly some interesting things we could do there.
Cool, thanks. I didn't mean to imply that those social conventions I was talking about were justified, just that they seem to exist, and maybe they exist proportional to loudness.
Yeah, I think we should really think hard about that and how we weigh the different constraints. And I think Ian's point about clusters is really good. And if we want to constrain the baryonic effects and the scale and redshift and halo mass depending on the effects, we need the clusters and we need the other probes.
I was just going to say a more general comment that I find it hard now to not, it's already apparent, I guess, even here on how we talk about results, on not cherry picking, because the reality is that all of these probes kind of have their real flaws that we have to tackle in the next decade with the incoming data. So clusters have baryonic effects as well. Importantly, in clustering and lensing, you need to worry about galaxy bias and assembly bias and galaxy lensing. And I guess we're really it's a good time to be a cosmologist because we have so much work to do to really show the robustness of all of these probes. And on the IA front and what we can expect coming, so I've been working on IA direct detections with DESI, and I really second what Alexie says about thinking about this with another survey, because we can already see that what we're going to get from DESI probably doesn't meet what we need for lensing surveys in terms of intrinsic alignments.
I guess no one at any point defined intrinsic alignments. I guess it's cosmic shears works by measuring the shape of galaxies that they get squashed when they get lensed, and then they take power spectrums to see how much the squashing at different points in space is related to each other, and therefore you're starting to get information about the matter distribution. Intrinsic alignments are just that galaxies might be similarly squashed intrinsically because of their environment, because they might be being pulled, like the galaxy being pulled by a local overdensity rather than the light from the galaxy being pulled by an overdensity. There was some mention in the text chat, I think, about whether hydrodynamical effects are actually relevant to intrinsic alignments, that whether gravity only is enough.
Well, I think it's clearly demonstrated that there can be significant misalignments between the optical component of a halo in your simulation or the gaseous component and the dark matter halo. So at the moment, I think all the intrinsic alignment models that are based on simulations are using links between large-scale structure and the halo alignment. But if there's a significant misalignment between the galaxy and the halo, then you're in trouble. I'm not sure what the consensus is between the different hydro simulations. It may, perhaps in the same way, it's similar to the baryon, gas expulsion question, in that there could be variations from study to study. But one thing we know for sure is that there are large misalignments. That's a clear statement. So it would be good to have observers, I think, test their marginalization procedures against hydro simulations and see whether they can take out the effect against all manner of different simulations. And if you can you can recover the truth against Celestris and against Eagle and Flamingo and then maybe you have some confidence that you're doing it in the real world. It's just a suggestion.
Let's move on to theory then. So the two things, well, the one thing that was kind of talked about the most, maybe surprisingly, is neutrino masses in this text discussion. There was consensus that if you don't change anything, neutrino masses can't help the S8 tension very much. But then there was a little bit of kind of like exploration around that about, well, the reason for that is that you need greater than 0.3 electron volt sum of neutrino masses in order to help with S8. So first of all, maybe let's just talk quickly about why one even expects a large neutrino mass to help with S8. And then let's talk about why greater than 0.3 electron volts is probably not allowed by data, but maybe is allowed by data. So Vivian, do you want to tell us why neutrino masses, a priori, before you've got any observational constraints, are relevant to S8?
I mean, the logic is that if S8 is due to, if you have to solve S8 by suppressing power, this is exactly what you expect from neutrino mass, from the fact that neutrinos are massive. So at late times, as they become non-relativistic, they're going to suppress the growth of structure. So, in fact, it's one of the extensions, if you wish, of the standard model that we are expecting to detect or that we're expecting to exist. So if someone tells you I've measured the suppression of power at small scales, the first thing that you should think of is it neutrinos? And unfortunately, the amplitude of the suppression that is required to explain the S8 tension is just too large given the constraints that we have. Because neutrinos, as they become massive, not only suppress the amplitude of structures at small scales, but they also change the omega matter. Essentially, now you have an additional non-relativistic species at late time, and that changes omega matter. And we have constraints on omega matter from BAO, Planck and BAO combined, that excludes too large a neutrino mass. So what you would need to do if you want to make neutrinos viable again would be to say maybe there is something that also affects the expansion rate at late time. So what if dark energy has also a weird shape or something like this? Then maybe you could compensate the effect that neutrinos have on the expansion history and still get the effect on the amplitude of the structure at small scale. Or other things would be playing with some systematic effects in Planck, for instance, A-lens and so on. That's another aspect.
Cool. Yeah, Ian, you mentioned a specific paper from about 2018 where you said if A-lens is treated as a free parameter, kind of like play the game of saying let's pretend it is a systematic, and if that systematic gets fixed by picking the preferred value of A-lens, that you actually do allow a larger neutrino mass. Do you want to quickly go into that?
Yeah, and it's not an idea from me. This is in the Planck papers themselves, actually, that if you plot the residuals of the primary CMB power spectrum against the best fit lambda model, the best fit lambda CDM model, you can see that there's a so-called smoothing of the peaks and troughs at high multipoles. So there's a clear modulation, if you want, and it looks like the effect of CMB lensing. That is, if you don't calculate what the CMB lensing amplitude is, but you let it float, then the Planck data prefers a value of 1.2 or something like this relative to what it should be. Another way to say the same thing is if you analyze one half of the Planck data from L of 0 to 1,000 versus 1,000 to 2,000, something around that, they give somewhat different answers for the best fit cosmology. The side that's low multipoles is in good agreement with WMAP, which is closer to the large-scale structure data, not fully consistent, but much is closer. So the tension is reduced. The tension strengthens when you include the high multipole, high angular resolution data from Planck. But we have measurements of CMB lensing which show its amplitude is in agreement with Planck. So that's the interesting point. So you know that it's not a physical issue going on here with CMB lensing, but one could interpret it as some other form of systematics in the high angular scale, small angular scales, that's not modeled correctly. In any case, there is an asymmetry that hasn't gone away. That's still there. And if you try to marginalize that out, then all kinds of funny things happen. So one is you actually prefer a relatively highish neutrino mass. You could also interpret the asymmetry in other ways. For example, a closed universe that's been discussed, a running of the scalar spectral index, all these sorts of things. And they're all sort of marginal to sigma effects, but that's kind of the level we're talking about here as the tension. So it's still something there. I'm not hanging my hat on it or anything like that. But in the discussion of an open discussion about systematics, there may well be relevant systematics on the CMB side that are just as relevant as any of the other ones we've been talking about in the context of cosmic shear and so on. And once you do that, as I said, if you allow that to float, the neutrino mass, that part of parameter space opens up. And the combination of A-lens and neutrino mask solves everything if you want it to go that route.
So that's the crucial last point. So if you do this, the allowed maximum value of the neutrino mass actually does get large enough that if you allowed that value of neutrino mass in a cosmic shear analysis, there would be a region of a neutrino mass and S8 contour plane where Planck and Kidd-Stairs and everything are just like completely on top of each other. Is that the statement being made? Okay.
That's right, yeah. And I was going to say that it's not just that it's allowed, it's actually marginally preferred. So that's where the maximum posterior is around 0.3, something like this. So yeah, it's an interesting thing. But
a few times a particular plot from a paper that was analyzing ultralight dark matter in the context of kind of the power spectrum and suppression and whether it can help with the S8 tension was brought up. I guess it's probably worth just going to this plot and having a look at it. Ultralight dark matter is obviously a model that is motivated in and of itself, and maybe it's even the correct model of the universe, but it's also good here, I guess, as just a representative of what a model that suppresses the power spectrum on small scales needs to do, because there are other models that are kind of very similar in terms of their phenomenological effect.
And I agree that this is just a representation of what the model needs to do. And if I can just take a step back for a minute, you have two sorts of models that have been invoked. You have some that are genuinely sort of like suppressing all scales in a redshift dependent manner. So for instance, I'm thinking of changing the growth factor in the late universe. So really changing all scales in a scale independent manner. And this is interesting because you could also potentially explain LN, so there is some ground this way. The alternative, and more motivated by particle physics in a sense, is to say maybe dark matter is not just called dark matter, there is some other component, maybe it's unstable, maybe there is some component of warm dark matter, or maybe there's some component of ultralight axion, and this is what we are looking at the moment, and they lead to similar sort of effects, except maybe in the details of the redshift dependence, the scale dependence, you would be able to discriminate the models. So this is why it's interesting. It's important to know what we're talking about also when we're talking about S8 versus when we're talking about the true tension with each experiment. But if we look at this plot and we take as granted that what we're talking about is S8, what you want to do is suppress the amplitude of the power spectrums on scales that overlap with this gray shaded region. And here the plot is a bit complicated. There are many masses, but it shows you that as a function of the mass, you're going to affect different scales, and then as a function of the abundance of that axion-like particle, you're going to affect the amplitude of the suppression is going to be more or less big, and it's going to be really similar to other models that may play with. For instance, you could call this a fraction of warm dark matter and play with the mass of warm dark matter and have very similar effects. And so now if we get into the nitty-gritty details of what mass we need, it's really where it's becoming more complicated, because if we ask for S8 itself, for instance, a mass of order something like 10 to the minus 28 eV, I think is this pinkish light purple color would be what you would need. Like here you would have a suppression that occurs within a scale that is being measured by S8, and given an abundance of a few percent in something like 5% off the top of my head of that ultralight axions, you would be able to explain a lower amplitude of fluctuation at small scales. And in these models, what's interesting is that they are imprinted at fairly high redshift. So Lyman alpha, for instance, would be able to see whether such a component exists. While other models that have a stronger redshift dependence, so I mentioned growth factor or decaying dark matter as well as the like, these models tend to push all the suppression at much later time. So this is one way of discriminating two categories of solution. If we see something at early time already, then we know hints towards, maybe a ultralight action, maybe a warm dark matter component, something like that, or an interaction. Something we have not mentioned is in the context of the H naught tension. Also, people are looking at whether there could be some dark radiation in the early universe, and that could also have interaction with dark matter, and that also would lead to something that looks like ultralight action that we're looking at and present at early time.
Okay, so I guess maybe two things that are worth bringing up. One is that I guess with warm dark matter, ultralight dark matter, blah blah blah, we've reached an era where it can't be all of the dark matter because of various constraints, but it having some subcomponent of the dark matter that is warm or is ultralight might have an impact on the S8 tension without breaking the other stuff that it got ruled out because of on perhaps even smaller scales like subhalos and these things. Which the other thing, I guess, just quickly, the reason ultralight dark matter has this drop is that it's so light that its de Broglie wavelength is large enough that it's kind of large on these scales on the x-axis here. So if its de Broglie wavelength is that large, it can't cluster smaller than that.
Right, exactly. And you could imagine, here we are, I pointed out 10 to the minus 25, but if we were to do the real analysis with cosmic shear data that actually have support at somewhat smaller scales, that mass can actually change, but the physics is the same. Still some sort of de Broglie wavelength like behavior that suppress power. Yes.
So I guess maybe a question we can't go into now, but maybe in the live discussion is, like all of these other things like galaxy clusters, are they also going to be alleviated by just a suppression on these scales? Because if so, then great. If not, then I guess it's a bit like the systematics. We can't solve all of the S8 tension with one systematic. We can't solve it all with one ultralight axion.
If indeed it's sigma 8 that matters for clusters, I've not really thought about it deeply, but my naive guess is that yes, it's possible that just one new physics work. But this is maybe me just making some wishful thinking.
All right, so let's now go on to the future of S8 and stage 4 clustering large-scale structure experiments. It seems like maybe at the moment, at least with cosmic shear, maybe not with galaxy clusters, but modeling is more important than data systematics. Presumably in the next generation, as the data gets better, once the models have caught up, the systematics will become the big issue at the moment.
But stage 4 is not the future. Yeah, stage 4 is not the future. Stage 4 is here because DESI is a stage 4 survey and is underway. It's the first stage 4 survey, and we are analyzing Y1 data. The paper's expected next year. And I think DESI is going to have a really big impact in this S8 question, and I'll just go through a list of different areas that DESI is going to, I think, give us some really interesting results. First of all, the RSD measurements. I'm not involved in those, so I won't talk about it. We'll have new lensing clustering results and updates to the 3x2 point in terms of the lensing and clustering. We're not going to redo the cosmic shear. We'll also explore the scale dependence of the GG lensing and the relationship between GG lensing and clustering. In addition, we're going to do things that are pretty novel in terms of we're going to use all of the lensing data sets and explore the consistency between the different lensing data sets. That's a big part of our effort. We're going to use common pipelines to measure all of these things that are tested on simulations. We also have new modeling efforts based on simulation-based modeling. Again, tying into the idea of trying to test the different scale dependencies of these questions. And then something that's not well known because DESI has only discovered this recently, and we have a big effort now on this question. DESI may be poised to play a really important role in the PhotoZ question for the PhotoZ calibration of lensing measurements. DESI has collected 200,000 new redshifts in Cosmos and XMM calibration fields, and we're trying to understand how useful these are going to be, but this is a lot larger than any of the existing calibration catalogs. So we may, in 1 or 2 years, have something really important to say on that front. DESI's really well posed to put new constraints on baronic effects, coming both from the new DESI data and modeling efforts, and then constraining IA models, which is something that Alex is interested in, has talked about. So yeah, stage 4 is here.
If someone is a PhD student or something right now, and they really are fascinated by the S8 tension, and they want to be working on modeling or data systematics or something to understand it better, what are the things they should be reading in the evenings, reading about or working on?
I think it's exciting because there are lots of different angles we need to think about, like what Vivian was talking about, thinking about models that might fit the observations that we're seeing. If we can predict that we need a power suppression, what are the physical models that are non-standard that might fit that? There's new data sets, as Alexie talked about, and those can be geared towards making new observations of cosmological constraints or using the data to do better in other standard probes already. So I like the helping the standard probes. I think I'm a little obsessed with weak lensing, but across the board, there's exciting things that whatever your type of interest is, you can find something and gear it towards the S8 tension.
Yeah, my comment was on the line of work more and study more systematics, because we're gonna really they're gonna be painful for stage 4, and they are already painful, I guess, for DESI. And so things like baryonic effects, intrinsic alignment, photo-Z errors, all these things, we need to control them at a level of accuracy that is unprecedented for these next generation surveys. We need more work into understand what are the errors and uncertainties in our model, and how do we embed these uncertainties in our inference, in our pipeline. We need to be systematic in this. And so I hope that in these next months or years we can work as a community more in this.
Yeah, I think we've discussed there being differences between the different probes at the moment, and we're not exactly sure what that means, whether it's different systematics or differences in modeling. I think one of the nice things about the models that are being developed now is that they can be projected in so many different ways. So we take the same simulation or the same baryonification approach, and you can project it into shear, but then you can also go to SC, you can go to galaxy lensing potentially, you can do lots of things, and it makes it a very nice way to talk in a sort of consistent, coherent way, whether there are tensions, at least from the modeling side, between all these different probes, I think. Because at the moment now, when you find a difference, you don't know if it's down to maybe the modeling choices, and when I'm talking modeling, how you implement the baryons, how you implement the intrinsic alignments, all these sorts of things. At least if we have a consistent theoretical framework behind it, all of these things that you just project into the observable space in all these different ways, at least you know that angle is taken care of, and that any tensions that are then remain are real, at least as far as the observations go. And at the moment, we all have our own little theoretical tools for analyzing our own data sets, and they're quite distinct. So I'm quite looking forward to a homogeneous approach on the theory side, to be able to project the same model for the universe in so many different ways. I think that's our future, probably, on the modeling side.
Yeah, I was just going to say, maybe on the theory side, there's two things that I want to say. The first thing is it's not enough to just explain. I say we have to make predictions, and it's for the next generation surveys, and as for linear cosmologists, as I'm calling myself, goes, then we have to learn how to really get to the precision or at the theoretical prediction level that isn't required for next generation. DESI is ongoing, but Euclid also is coming, etc. And the second thing is something that I think is interesting on the theory building model building side, is to connect this with the H0 tension, something we have not discussed at all, and I understand, but it's really interesting because it's these two when we look at each other very naively, unfortunately, these two tensions sort of conspire against each other, and so there is also a lot of interesting things to try to learn in a more global cosmological tension context about potential near physics.